Okay, let's take a couple minutes here to wrap up chapter 9, our electron stuff. I think I touched on this already, but just to review real quick. We can predict some things about, a lot of things from the periodic table. One of the things we've been talking about was atomic size. This is ionization energy, but if you remember the chart for atomic size, we know that size increases as we go down and to the left, right? As we get down here, things like francium, cesium, these are very large atoms. That means from the center of their nucleus to all the way to the outside of where as far away their electrons would be buzzing, that diameter or that radius is very big. Fluorine's very small, helium's very small, that kind of thing. Now, related to that are a couple other things, one of which is what's called ionization energy. And when I'm talking about ionization energy, what I'm talking about is how easy it is to knock an electron free from one of its shells and have it go out somewhere and cause something to happen. So if something has a high ionization energy, that means it takes a lot of energy input in order to turn it into an ion. In other words, a lot of energy must go into it in order to knock an electron loose and cause it to go somewhere. So fluorine has a very high ionization energy. It takes a lot of muscle to knock out an electron from where it's buzzing around in fluorine. Whereas way down here, as we go down to the left down here, this decreases. Notice the arrows come together to increase on that side. Way down here, francium is pretty loose with its electrons. It's kind of easy to jostle some electrons loose if we need to from francium. So ionization energy increases as we go up and to the right. So don't worry about these graphs. They're interesting, but past what we need to do. So I won't make you know anything about those. If you take a look at here, just remind me, if we look at magnesium, which is right here, phosphorus, which is right here, which one has a higher ionization energy? Which one? Phosphorus, right? Phosphorus is to the right. They're in the same row. That's to the right. We're looking at anything to the right and or above of the other one. So phosphorus would require more energy to knock its electrons out. Okay? AS or SB, we're right here. Arsenic, right, would actually have a higher ionization energy. Nitrogen or silicon, which one of those would have a higher ionization energy? Nitrogen. And oxygen or chlorine. It's hard to tell. Notice that neither one is really above and to the right and or to the right. They're kind of just at a diagonal. If you imagine starting here and working your way down, they're sort of right in line with each other. So there is a way to tell, but not just according to using the table and predicting things like that. So we'll just say not enough information on that one. All right. The last thing that we're going to use, very similar to this, kind of up and to the right, down to the left kind of thing, is to predict one more that's going to become very important as you go into the next chapter, and that is what's called the metallicity of certain elements. We know there are metals and there are nonmetals. And you should know now how to find them, right? The stair step divides them. You've got some of them touching the stair step, that little zigzag. Those are metalloids, and then to the left are your metals, and to the right are your nonmetals. Well, realize that metallicity is a relative term. You can have two nonmetals and have one that's actually more metallic than the other, even though neither one of them are actually metallic. You see what I mean? It's just a comparison. Like carbon and oxygen, you'll find that carbon and oxygen are both nonmetals. But out of those two, the one that's more like a metal than the other one is carbon. Okay? So we can remember the properties of metals, if you think back. Okay? We know that they're malleable and ductile. You can bend them. You can turn them into wire. They're kind of flexible kind of stuff. You don't seem like it, but it is. They are able to change their shape. Shiny, reflect light, lustrous, these are all properties of metals. Conduct heat and electricity. It forms oxides. Okay, it likes to react with oxygen. Forms cations in solution. Remember, positively charged, all the metals are usually cations. They're always usually oxidized, meaning they, remember, lose electrons oxidized, right? Usually they always give up their electrons in chemical reactions, so they're always usually oxidized. Nonmetals are their exact counterpart. They're the opposite of that. Okay, they're generally reduced. All right, that being said, if you look at the table here, notice where these arrows go. The more we go this way, which makes sense, it wouldn't make sense to go the other way because those are nonmetals, right? So the more we go down and to the left, the more metallic the character becomes by definition. The more of those criteria that you just looked at seem to be fulfilled. So francium is sort of like the most metallic that you can have on this particular table in terms of what metallic stands for, those things, those characteristics that I just showed you. Fluorine, in terms of things that aren't noble gases, fluorine would be the least metallic. Okay. Now realize then as we move down to the left, you can have fluorine and sulfur, for example. Both of them are obviously nonmetals, but if you had to compare the two, you would say that sulfur is actually more metallic than what fluorine would be. All right. So in this case, if we have tin or tellurium, which one is more metallic? Here's tellurium here, here's tin. Tin, that makes sense. You can just look at it and know that that's a metalloid, and that's actually a metal, so obviously the metal is going to be more metallic. But look at it, it's to the left. Okay. Silicon or tin. Here's silicon, here's tin. Tin again. Okay, it's down, it's below. They're in the same, and we're moving this way across the table. So we're looking at down and or to the left. Bromine or tellurium. Here's bromine, here's tellurium. Tellurium, right? Selenium or iodine. Here's selenium, here's iodine. Can't really tell. You know where the most common place in your house where you're going to find selenium? In one of the household products that you use a lot? Anybody know? Shampoo. Anybody ever watch that movie Evolution with David Duchovny in it? Yeah, they mentioned it. That's how they kill the giant monster at the end. It's very unrealistic, but it's a let me just point out, just so you know in movies, this is the way I watch movies, and hopefully at some point you will learn to watch movies in the same way that I watch movies. The chemistry is completely flawed in this whole thing because we are an oxygen-based life form, right? Excuse me. And this is ridiculous. I don't even know how he came. Oh, sorry, not oxygen, carbon-based life form. We're a carbon-based life form, and one of the things that's very toxic to us is arsenic, right? So if you go down on the table, down 2 across 1, you get arsenic. Well, the genius behind the chemistry theory in this particular movie said, oh, well, since arsenic kills us, if we take a nitrogen-based life form, which is what this alien was, go down 2 spots and 1 to the right, we get selenium, so selenium must kill this thing. Of course, that doesn't make any sense, but it worked. So then they were like, where can we get all this selenium from? And then the 2 geniuses of the class, who were really the 2 dumbest kids in the class, they said, we'll just steal a bunch of shampoo. They took a whole bunch of Head and Shoulders and dumped it into a giant tank and collected a bunch of selenium, I guess, and shot it at this giant monster and killed it. But anyways, then we get into the whole evolution side of things and the lack of selective pressure on the whole movie, and it was unrealistic. Anyways. All right. So that's that chapter. Any questions about any of that?